Imagine taking the plunge, crossing the event horizon of a supermassive black hole. We know escape is impossible, and the journey ends at the central singularity. But physicists describe this endpoint in dramatic terms, sometimes calling it the end of time. What does that really mean? How can time itself end? And what's this bizarre idea about space and time swapping roles inside? Let's start with that swap. It's not just a metaphor for an inevitable fate. It stems from the actual mathematics of Einstein's general relativity. Outside the black hole, we have one dimension of time and three of space. We can move freely back and forth in space, but we are compelled to move forward in time. The math reflects this. The time part of the space-time equation has a different sign than the space parts. But when you cross the event horizon, the extreme curvature causes the mathematical structure of space-time to fundamentally change character. The roles flip. The coordinate representing radial distance r, distance from the center, takes on the mathematical properties of time. Its sign in the equations flips. And the coordinate t, which represented time outside, takes on the properties of space. What does this mean practically? Inside the horizon, moving towards the singularity becomes your unavoidable future, just like moving towards future t is unavoidable outside. Just as you cannot stop time from passing normally. This isn't just because gravity is strong. It's because the direction inward becomes the time-like direction of travel for everything. Can you then move sideways or backward in t, the coordinate that used to be time? Since it now behaves like a spatial dimension inside, theoretically, yes, you could move in different t directions locally. But here's the catch. It doesn't help you escape. Because r is now the effective time dimension, any movement you make in t still happens while you are inevitably carried forward in your new time, towards smaller r, and the singularity. This role swap isn't caused by your speed. It's an intrinsic feature of the space-time geometry inside the horizon, created by the black hole's mass. Now, what about the view of the outside universe? It's said that as you fall towards the event horizon, looking back out, the universe would appear increasingly sped up and blue-shifted, light arriving faster and with more energy due to gravitational effects. Does this mean you get a fast-forward view of all of future history, right up to the end of the universe itself, just before you cross the horizon? The answer is no. While the effect is real and dramatic on approach, you only see the light that could reach you before you cross the horizon. You cross that boundary in a finite amount of your own time. Once inside, you are causally disconnected from the future of the external universe. Light from distant future events can no longer reach you. Your view becomes dominated by the light and matter falling in with you, all converging towards the singularity. You won't witness the universe's final moments. So why is the singularity called the end of time? It's because, in the framework of classical general relativity, the singularity, at r equals 0, is where the observer's world line their path through space-time abruptly terminates. Space-time curvature becomes infinite, and the known laws of physics break down. For the object or observer reaching it, there is no after within this model. Time, as experienced along their path, ceases to progress, because the path itself ends. Does this mean space and time are fundamentally the same thing? Relativity certainly showed they are deeply interwoven into a single fabric space-time. How much time or space you measure between events depends on your motion and gravity. The swap inside a black hole dramatically illustrates this connection, but they aren't completely identical. Time still seems to have a forward direction outside black holes, linked to causality and entropy, which space doesn't inherently possess. They are two related but distinct aspects of the same underlying geometry. And what happens to space-time when it's squashed infinitely at the singularity? Classically, it's an infinite stretching and squeezing, a point where the geometric description fails utterly. This is where quantum gravity must step in to provide the real answer. But within the classical picture that describes the journey from the horizon, the singularity marks the point beyond which the observer's timeline, their passage through time as they know it, cannot continue. It is, quite literally for them, the end of their time. Let me know your thoughts in the comments below. Subscribe for more explorations into science and philosophy. Thanks for watching, and see you in the next one.